Good evening, everyone. Beautiful evening to you guys. How you doing? How was your Saturday? Hope you enjoyed your day. Hope you are doing great. How are things at your side? We don't have much time. We will be starting immediately. How did you guys find the quiz test? Hope you enjoyed it. Hope you enjoyed the quiz. Hope you enjoyed the quiz test. Okay, you enjoyed it, bar. Okay, okay. Okay. Yesterday, you guys said like it was easy peasy. So, and I felt you guys are supposed to say easy peasy tonight again. Okay. So, anyway, one of the main thing we're doing is we're introducing you gently to probability because, as I told you guys already, there are lots of questions that can come out on this topic. It's a very examinable aspect of statistics, and it's very very versatile. There is a lot of scope under probability, and tonight, without wasting time, we want to get into other scopes under probability. You guys are going to enjoy every bit of it. It's very simple, very easy. All you need to do is to just pay attention. I can assure you, it's very very easy. All right. So in today's class, we're going to start with uh, complementary events. Complementary events. All right. Uh, when we talk about complementary events, it's a very vital part of probability, and I will tell you why. Some of the questions we solved yesterday and the day before yesterday, you would have gotten it quite very simply if you made use of this concept called complementary events under probability. It's very, very essential you understand it. So, what is complementary event without wasting time? Now, when you talk about complementary event, it's simply just the same knowledge you have on complements under set theory is the same uh, is the same concept right here. So let's take for instance we have an event A happening. All right. Let's say event A existed. Let's say we have event A. So how do we write the complement of event A? Well, we'll go on and say A complement. So right here, this is the complement of this event A happening. I can go on and on to give you lots of examples on complementary events. We'll be dealing with several examples and you will be able to see how this thing really works. So without wasting time, one thing you need to know is complementary events. Look at it. Look at what I wrote right here. I said event A union event A complement is equals to the sample space. This means that when you have an event A happening, if you make a union of that event with its complement, you will be getting the entire sample space. That's the meaning of what I just wrote right here. And this brings us to a mathematical implication of this, which is that you can obviously go on to find the probability of A complement by doing just this. 1 minus probability of A. This is the key that you need to always take note of. Look at it. We have event A. We have event A complement. I told you guys already here that the union of event A and event A complement is the entire sample space. Meaning that, for instance, let's say we have, do not forget, guys, I told you already that the total probability in any event, any experiment, is always equals to 1. Anything beyond 1, it's no longer dealing with probability. You must never have anything outside 1. 1.1, 1.2 is no longer probability. This means if you have an event A, let me tell you what this means. This means probability of event A plus probability of event A complement is equals to 1. Now look at what I wrote here. I told you guys already that A with union of A complement is the entire sample space. Meaning that the probability of A happening plus the probability of A complement happening will be equals to 1. Alright? Now, you use this majorly when you want to find the probability of the complement of an event, and you don't want to go on and be going on with a lot of long solutions. So what you do is you just go on to subtract the probability of the event A from 1. You will get the probability of A complement. This may look abstract right now, but when we start solving, you will see how very interesting this is. But one thing I just want you to understand is, take note of these two formulas. This is, of course, the bedrock on which this one was defined. Probability of A plus probability of A complement is always going to be equals to 1. That means probability of A complement will be 1 minus probability of A. Let's get right into it. The first question right here. Of course, I love how you guys always send me great answers. I want you to do the same thing this moment. If probability of A, guys, equals to 0.7, find probability of A complement. Oh yeah, shoot me the answers in 2 seconds. Oh yeah, this is the first question. Probability of A is 0.7. Find probability of A complement. What's my answer? I'm waiting. All right, I can see. Great. That's great. Now, one thing you can see you guys did is that you went on to say probability of A complement will be equals to 1 minus probability of A. That was 1 minus, since we agreed probability of A being 0.7, that was 1 minus 0.7, that was equals to 0.3. That's the correct answer. Good. All right, let's see another question very quickly. If probability of A complement is equals to 0.25, out of screen, right? All right, go on to find probability of A. We're warming up. Okay, what's probability of A? All right, so I can see you guys are flowing with what I just explained. So you went on to say the probability of A will obviously be 1 minus probability of A complement, and that was 1 minus 0.25, and that was 0.75. Great. Now, let's now move a bit further. Look at this question. A die was rolled. A die was rolled. A die was rolled. Find the probability of not getting a 6. So a die was rolled. You have to find the probability of not getting a 6. Find the probability of not getting a 6. Now, I'm going to use this question to give you great understanding of using complementary events. Look at this question right now. A die was rolled. You have to find the probability of not getting a 6. Of course, you know in a dice we have 1, 2, 3, 4, 5, 6. So when they say find the probability of not getting a 6, I'm sure you guys agree with me that all these ones are what are the elements of the event space. Now, if you went on in using all the solutions we did yesterday and day before yesterday, what you guys would have done would have been to say the event space here was 1, 2, 3, 4, 5, and then you would have said the number of elements in the event space was 5, and then you would have said the total number of elements in sample space was 6. You would have said the probability of this event is 5 over 6. You would have been correct. But let us apply the knowledge of complementary events. So the question now is, if you have an event, probability of not getting a 6 as the event. Let's say an event A was not getting a 6. All right? Guys, I want you guys to answer me. What is going to be the, or let me just say, sorry, not probability. Let's say the event A. Event A was not getting a 6. What's going to be A complement, guys? What's going to be A complement? If A is not getting a 6, the event A was not getting a 6, what's going to be the complement of that? The complement of that will obviously be getting a 6. Getting a 6. Complement just means the opposite. So if you said getting a 6, every other thing in the sample space apart from that event is a complement. As I told you already, the union of an event with its complement is always equal to the sample space. So if the event was not getting a 6, that means the complement will be getting a 6. All right? Getting a 6. Now, if you get that right, that means you were told to find the probability of not getting a 6. Now, what you could ask yourself was, what's the probability of getting a 6? What's the probability of getting a 6? That means I go on to find the other side of things. What's probability, since probably it may be a bit longer, bringing out my event and all those things, just go on to say what's probability of getting a 6. That means what's probability of A complement. In this case, by the way, let me quickly say something. It doesn't have to necessarily be that A was not getting. It's possible that A complement could be not getting a 6 and A was getting a 6. All those things are all based on the context of your question. You don't have to have a rigid mind that A represented not getting a 6. In another question, it's possible that A will represent getting a 6 and A complement will be not getting a 6. So understand the context of the question. The probability of A complement, that is getting a 6, will obviously be getting a 6. You know this one obviously that we have only one event as 6. That will be 1 over 6 as the probability. So for you to get the probability of A now, which was not getting a 6, using this experience of complementary event, it would have been 1 minus 1 over 6. That would have been 5 over 6. You can see it's the same answer if you move through complementary events or you move through the normal way. Now, I'm sure many of you will be wondering, why do we need to deal with complementary events if we could easily just do it like this? Guys, I need to tell you, you will see many questions that you actually dare not move through this method, this normal method, in which it's very impossible for you to bring out, or either impossible or very tedious to bring out the event space. And all you would have needed to use would have been this complementary event. Let me say that one more time. You guys may be wondering, why is it that we have to use complementary events when we could actually get priority of this event dealing with this method that we have been using from day one of these our classes? Now, this is an easy question. There are other questions in which this whole thing, the event space, will be very tedious to bring out. So in that case, you will just need to bring out the complement, and using that complement, you will get your answer. You will see examples like that very soon. Just stay in touch with me right here. You will get to understand what I'm saying. I just want you to get used to the whole concept with these simple examples. Now let's go on to solve another one. Now, find the probability of not drawing a heart. That's a card question. Find probability of not drawing a heart. Of course, we have done a little bit of cards yesterday. So the question just said, find the probability of not drawing a heart. Find the probability of not drawing a heart. This is obviously a question under cards. Now, many of you, of course, if you have been attending the classes, you understand all the constituents of playing cards. So the question is, instead of going on to find all the other event space or what is not a heart, all I need to do is, I know my event now is probability of not drawing a heart, but so the event heart, the event that has to do with heart when drawing cards, what's the event space? Or let me just say, what's the number of elements of that event space? Number of elements of heart, we did it in probably yesterday's class. We have 13 hearts. Am I right? Out of 52 cards. The sample space for a playing for pack of cards is obviously 52. Now, so the event of drawing a heart, the number of elements of that event is 13 because we have 13 playing cards that are hearts, and then we have sample space of 52. The probability of drawing a heart is what? Probability of drawing a heart is 13 over 52. Now, look at this example. If you want to go on to find probability of not drawing a heart without following complementary event, what you have to do is to go on to ask yourself, what are the other cards that are not hearts in a pack of playing cards? Now, of course, that will be 52 minus 13. If you go on with that way, you get your answer. Again, this is still another simple question, but you get to questions very soon where you will see that it's almost impossible for you to, almost either impossible or very tedious for you to use any other method apart from complementary events. So the probability of getting hearts is 13 over 52. So the probability of not heart now, not drawing a heart, will obviously be just 1 minus 13 over 52. So obviously, I told you guys one thing. Let me always do this with you people so that you can understand this very well. I told you that an event union the complement is equals to the sample space. This means if for you to confirm, because some of you, I don't want you to get confused. Don't go on to say not something. Not something will mean always complement. When you see questions, you understand better. Look at it. If you have an event, if you take the union of that event with the complement, if they do not give you the sample space, then that means that was not a complement. Look at this right here. If you draw a heart or not drawing a heart, if you take the union of the heart and not heart, of course that will be the whole sample space, because there is nothing else in that sample space apart from either a heart or not a heart. So this is a perfect definition of an event with its complement. All right, that's a good way to check and balance your work. Now let's move on with another question. You keep on understanding it as you keep moving. Now from 1 to 10, find probability of not selecting a multiple of 3. From 1 to 10, find the probability of not selecting a multiple of 3. So from 1 to 10, find the probability of not selecting a multiple of 3. From 1 to 10. So you have to find the probability of not selecting a multiple of 3. All right. So now this is another example. They said not selecting a multiple of 3. Of course, the complement here will be selecting a multiple of 3. So all you need to first of all look at the event. The event you are dealing with here is not selecting. That means not selecting. So in short, not a multiple of 3. Now, the complement of that event will be a multiple of 3. All right. Now, from 1 to 10, if you look at what are multiples of 3 from 1 to 10? We have 3, we have 6, we have 9. So obviously, a multiple of 3 for this event now, this event right here, the probability of selecting a multiple of 3, probability of this event, the complement this event right here, a multiple of 3, will be, of course, the event space is 3, 6, and 9. Number of elements in that event space is 3. I'm sure we have done that yesterday, so I don't want to spend much time on that because I believe you people should have gotten the hang of what we're doing. So this event will be 3 over, of course, the total number of elements in the sample space, that's NS. The total number of possible outcomes is actually 10. I'm sure you agree with that. So that will be 3 over 10. So a multiple of 3, the probability of selecting a multiple of 3 is 3 over 10. So for you to find the probability of this event now, which was not multiple of 3, will be 1 minus 3 over 10, which will be 7 over 10. So this is the general concept around complementary event. You just need to understand how it works and you will never go wrong. All right, let's see another one now. A fair coin is tossed 3 times. 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 Find the probability of at least 1 head. And please do not use the method we used yesterday and the day before yesterday. Make sure you use complementary events. So a fair coin is tossed 3 times. Find the probability of at least 1 head. Do not use the method we used yesterday. I want you to use complementary events. So you have to find the probability of at least 1 head. All right. Anybody with an answer yet? Probability of at least 1 head. Don't use the approach of yesterday. Of course, I'm sure everyone that attended the class yesterday should be able to solve this using the straightforward method. But of course, complementary events are also straightforward, but I want you to learn how to use them. So go on and use complementary events to solve this. All right. I'm seeing some answers. Okay. Looks like okay, so we can easily do this by just first of all recognizing what was the event. Of course, at least 1 head was the event we are told to find. At least one head. All right. This is what we're trying to find, probability of at least one head. If you look at this event and recognizing the sample space of tossing a coin 3 times, of course, you know that already. I'm sure you remember that because we did that already. We have HHH, we have HHT, dot, 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 on and on. We have TTT. Now, looking at all this, the probability of at least one head, normally, if you wanted to solve this using the other method, you want to go on counting all that had at least one head, according to what we did in previous classes. But on a complementary event, you don't have to do all of that. All you just need to recognize is what is the let's call this event E. So the probability of this was event E now. So you need to just go and find out what was the complement. So the complement of at least one head would be no. Who can tell me that, by the way? Let me not say it yet. What's going to be the complement of at least one head? At least one. What's going to be the complementary event of at least one head? At least what's going to be a complementary event? No head, exactly. That's a perfect answer. No head. All right? No head at all. So if at least one head was an event, no head at all would be the complement. No head. Because at least one head means 1, 2, 3 heads are permitted. But no head at all will be the complement of that. And do not forget, I told you already, one of the best way to check this up is to go on and ask yourself, the 2 events I just mentioned are at least one head and no head. Do they form the entire sample space? If yes, then that means you are okay. If they do not form the sample space, then that means there's an issue with whatever you called the complement. So looking at this now, of course, no head at all. We have just an event. The event space there was only TTT. So instead of going on to be counting all the ones that had at least one head, all we're interested in is the complementary event, which is TTT. So I go on to find the probability of this complementary event, and that will be 1 because only 1 was there out of the total number of elements in the sample space. That was 8. I'm sure you guys should be familiar with this if you attended our classes before. Now, for me to now find the probability of the event we're actually asked to find, I just need to go on to find 1 minus the probability of the complement, which will be 1 minus 1 over 8, which will be 7 over 8. So this is how you make use of complementary events to deal with questions. You will see questions where it is actually impossible for you to go on to be counting. Very hard for you to be counting. So all you will need to rely on is complementary events. All right. Now look at this next question. Look at this. We have the probability of an event A being equals to 0.3. The probability of an event A is equals to 0.3. The probability of an event A is equals to 0.3. The probability of an event B is 0.4. Now, we're going to assume independence. That means they do not depend on each other. So the question is for you to find the probability that none occur. All right? Can you solve this? Look at it. We have the probability of an event A being 0.3, the probability of an event B being 0.4. We are told to assume independence. So the question is for you to find probability that none occur. Okay, nobody has gotten the answer. Let me go on and solve it very quickly because of time. Now, when you're looking at this, we said assume independence. The first thing you need to find out is probability that none occur. If you say this with verbally, that would mean probability that A did not occur and also B did not occur. That's not occurring. Probability of event A did not occur and probability of event B did not occur. That would be the way to say this. All right. Now, a way of writing probability of A did not occur will be probability of A complement. All right. So we go on to find probability of A complement. That'll be 1 minus 0.3. That'll be what? 0.7. All right. Probability of B not occurring. That'll be probability of B complement. All right. And that will be 1 minus. That's why we said assume independence. That means there is no dependency between any of these two events. That will be 1 minus 0.4. By the way, we'll be getting into independent events very soon. So you just need to sit back and be calm. We're going to get into that very soon. Now, if you look at this, this is obviously the event B not happening. Now you are told to find probability that none occurred. That means probability of none occurring means probability that A did not occur and the probability that B did not occur. So this obviously will be 0.7 multiplied by 0.6, which will give you 0.42. All right. Now you're learning. Of course, we'll keep pushing this further. You keep getting a better understanding. Just keep paying attention. Now, a very quick one right here. I want you guys to give me the answer in just 5 seconds maximum. If the probability a student passes is 0.8, what's the probability that the student fails? Oh yeah, 5 seconds. Thank you. If the probability that a student passes is 0.8, find the probability that the student fails. Of course, probability of the student passing, let's call it event A. We said it was 0.8. Probability that the student fails, that will be probability of A complement. That will be 1 minus 0.8, which will be 0.2. All right. Now, another question quickly, still on that complementary event. A die is rolled. A die is rolled. Find the probability of at most 4. Find the probability of at most 4. So a die is rolled. Find the probability of at most 4. What's your answer? Of course, I'm sure you recognize that it's very possible to solve this without dealing with complementary events. Probability of at most 4, meaning that, of course, you can easily bring out the event space of at most 4. At most 4 will be what? At most 4 will be 1, 2, 3, 4. This would have been the event space. If you wanted to pass through the method we used yesterday, and then probability of at most 4 would just have been 4 out of 6. That was simple, I understand. But I want you to use the concept of complementary event. What's going to be the complementary event of at most 4? So, of course, if at most 4, if the event was at most 4, so obviously the complement of that event will be not at most 4. So every other thing apart from at most 4, that's going to be the complement of the event. So, and obviously, not at most 4 will be 5 and 6. That will be the event 5 and 6. So if you go on to solve the probability of not at most 4, just trying to use the complementary event procedure, probability of not at most 4 will be, the probability of that will be 2, because you have 2 events. N of E complement there is 2. I don't want to be writing all those today because, of course, it's good for you to write it if you're in an exam, all right? But I would love you to, for today, I want us to delve into much deeper aspect of probability. So I'm sure you understand what I'm doing here. So this will be 2 over 6. All right. And for you to find the event now, since we know the complement to be 2 over 6, to find the event of at most 4 will be 1 minus the probability of not at most 4, which will be 1 minus 2 over 6, which will be 4 over 6, which will be 2 over 3. Does it make sense, guys? This is how you deal with complementary events in probability. Just go and find a complement, and the addition of the event plus the probability of the complement should always give you 1. So you just go on to subtract it from 1. All right. Now look at this next question. From 1 to 20, find the probability that of at least one multiple of 5. Find the probability of at least one multiple of 5. From 1 to 20, find the probability of at least one multiple of 5. From 1 to 20, so you have to find the probability of at least one multiple of 5 using complementary events, obviously. Using complementary events. So obviously, if an event is at least one multiple of 5, so obviously it will be no multiple of 5. That will be the complementary event. All right. So if the event is at least one multiple of 5, at least one, that means you must see multiple of 5 there. So more than one multiple of 5 is still accepted. So, but at least you must see 1. That's the event. So the complement will obviously be no multiple of 5. That means none multiple of 5. So looking at the sample space, we're dealing with 1 to 20. So you need to go on to find what are the elements there that are not multiple of 5. So non-multiple of 5 from 1 to 20 will be what? Of course, you have about the multiple of 5 will be, we have 5, we have 10, we have 15, we have 20. So at least one multiple of 5. This is the event space for that. All right. The complement of this will be everything apart from all this from that is in between 1 to 20, obviously. So anything here, like for instance, 1, 2, 3, 4, 6, 7, 8, 9, 11, and so on up until 19. So if you count the number of elements that will be here, that will obviously be the end of this E complement will be 16. So if you go on to find the probability of the E complement, that will be 16 over 20. Obviously, NS is 20. So the probability of the event E, which is at least one multiple of 5, will be 1 minus 16 over 20. That will be 4 over 20. Of course, this looks like we had the complement was even much more tedious than the normal method. But of course, I just want to establish the idea of complementary events in this class. So you would see a time when you would really need to use this. All right. Now let's see another question. So we have, let me see how we're going to do this. I don't expect anybody, because we have done something here already. So I expect you guys to get this one. So we have the probability of, this is the question, probability of A was 0.2. The probability of B, an event B, was 0.3. The probability of an event C was 0.4. So the question was, of course, as imagine all of these events are independent, all right? events A, B, C are all independent. So you have to find the probability that none occur. Find the probability that none occur. Find the probability that none occur, right? Find the probability that none occur. We have done this before, so I expect you guys to smash this. Probability that none occur. What's your answer? Okay, so how you solve this using complementary event? Obviously, you have to find probability that none occur. That means probability that A did not occur. Then probability that also B did not occur. And probability that C did not occur. So you need to go on to find what was the probability that A did not occur. That will be 1 minus probability that A occurred, which will be 1 minus 0.2. That will be 0.8, right? And then for this other one, this will be 1 minus probability that B occurred. That will be 1 minus 0.3. That will be 0.7. Then for probability that C did not occur, with probability that C occurred, 1 minus probability that C occurred, which will be 1 minus 0.4. That will be 0.6. So probability that none occur mean, of course, if you say this verbally, you will be hearing yourself say probability that A did not occur, and B did not occur, and C did not occur. That's the way you're going to say this. And since these events are independent, the probability that none occur will be 0.8 times 0.7 times 0.6. This will give me a total of 0.336. All right. So you can see how interesting this question is, right? All right. So this is where I'm going to hold up on complementary events. Of course, there are other questions, or probably let me give you one quickly so that you can see one of the very important use of complementary event. Let me just throw this one to you guys. In a single throw of 6 fair coin, 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 you'll see a very good use of complementary event right now. In a single throw of 6 fair coin, find the probability that at least one head shows up on a coin. Find the probability that at least one head shows up on the coin. So the question is, now you're dealing with a single throw of six fair coin, but to find the probability that at least one edge shows up on the coin. Now, I love that somebody was very bold enough to throw the answer in seconds. That's exactly what the knowledge of complementary events do for you. A very tedious question becomes so easy. Now, looking at this question right now, if you want to go through the method we were using yesterday and all the days, probably 2 days ago or so, it would have been very tedious. You are dealing with 6 fair coin. You're throwing 6 fair coin. That means you'll be having a situation where you'll be having H, 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 H. Can you imagine how tedious this would be? To even bring out all the elements of the sample space, you will be almost dead before you are done with it, right? Because it's so tedious. Your exam would have been done before you are even done bringing out the sample space. Very tedious. You bring out for 3, bring out for 4, bring out for 5, then bring out for 6. Now, of course, it's possible to solve, but very tedious. All right, jokes apart, it's very possible to solve it that way, but it will take a lot of your time. And that's the reason why you need to understand complementary events, right? Find probability that at least one edge show up. When you see the question, at least one edge, Of course, from your understanding of how all these experiments go, you know already that in a throw of any number of coin, you always have one thing. You always have a possibility of a possible outcome of all the heads being all of the events and also tail being all of the events. All right, you know this already. The rest will have tail, head. Some will have five tail, five. Some will have five head, one tail. From four head, two tail. You have different examples with different arrangements going on in your sample space. But when the question said at least one head, you know already that every other thing apart from this, apart from all tail, is actually at least one head. That's the reason why you need the understanding of complementary events. So what you just need to do is to understand, number one, you don't need to go on bringing out all the number of elements in the sample, sorry, bringing out all the elements in the sample space. I taught you already that when you have any number of fair coin, the general formula is 2 raised to the power of n. So obviously this will be 2 raised to the power of 6. That's how you're going to get the number of elements in the sample space to be 64. So you know already that you have 64 elements in the sample space, but you do not know now how to get at least one head, and you cannot go on to be bringing out all the elements. So you need the understanding of complementary events to solve this. So now, if you have 64 elements in the sample space, you know already that it is only one. Now, this is the event you were looking for is at least one head. This was the event you were told to find. The complement of this, obviously, will be no head at all, which is equivalent to saying all tail. Now, you know already that all tail, it's only one element that will always happen. If you are throwing 10 coin, it's only one element that will be all tail in that throw. All right, it's not it's a general thing. You will have one event as all head and one event as all tail, meaning that you can easily get the probability of this event. That means the event of the complement. You can get that to be 1 out of what is the total number of elements in the sample space, 1 over 64. All right, so you can get the complement, the probability of the complement. So since you can get the probability of the complement, all you want to do is to go on to use your understanding of complementary event, where you know that probability of the event plus probability of the complement will give you 1. So obviously, the probability of the event E will be 1 minus 1 over 64. And that will be what? Okay, we are out of the camera space right there. So of course, the probability of this event now of at least one head will be 1 minus probability of its complement, and that will be 1 minus 1 over 64, and that will be what? 63 over 64. Now, you understand that in an exam, or especially in an objective exam, you don't need to even use up to 10 seconds to solve this kind of question. I'm sure some of you, when you first heard me say in a single throw of 6 fair coin, you felt very like this is going to be a very tedious question. Of course, if you do not understand complementary event, it will have been super tedious, all right? Because you would have gone through a lot to get all the elements that, of course, at least one head will be 1 head, 2 head, 3 head, 4 head, 5 head, and 6 head. Going to count all those ones would have been tedious. But now that you understand complementary, then all you have to do is just do this, all right? So simple and straightforward. So let's get right into the next aspect of probability we want to deal with. So guys, do you really understand complementary events? Are you very grounded now? Can I get responses and feedbacks? How do you feel about complementary events? Are you okay with the explanation? Okay. Okay, you know what you're going to do, Enoch? You will have the opportunity of going through this video again. Every other person seems to really understand it. All right. So now let's go to the next. Let's go to the next question around under probability. All right, combination of events, combination of events, combination of events. Now, when you deal with combination of events, there are two things you need to pay attention to when you hear the word combination of events under probability. When we talk about combination of events, we mean how two or more events relate or combine with each other using set operation. And there are two scenarios you'll be dealing with. The first one will be the union of events. And I'm sure you can guess number two will be what? Intersection of events. These two things are very vital while dealing with events. These two things we just mentioned. So guys, I'm going to give you a very big expose on union of events, and you guys are I really want you to pay real attention. These are things that will help you to be able to juggle any question in any exam. Doesn't matter however they are trying to twist it. All right. Now, the general formula for union of events, of course, when you hear union of events, one thing you need to know is union of event has to do with you saying, for instance, let's say we're dealing with two events. Of course, union of events can be with two events or with three events or with more than three events. All right. Now, let's say we have event A and event B. When we say union of these two events, it will actually mean we're dealing with saying event A or event B or both of them or both occur. So that's exactly the concept around union. Union means we are saying event A or event B or both of them. If any of these things happen, we are dealing with, this thing happening is exactly the concept of union, where all these are the case. Now, I'm sure you guys already have a good knowledge on sets. So let's try and draw the set diagram, and let's say this was event A. All right. Now, if this was event B, let's say this was event A, let's say this was event B. All right. Now, I'm sure you recognize that this whole thing represents event A, the whole circle I just marked, and this other whole circle represents event B. And right here, this spot in between represents the intersection of both event A and event B. All right. Now, when we're dealing with union, I'm sure you guys understand how to shade. If I asked you to, you were asked to shade the A union B, if you wanted to represent A union B, being shaded, of course, you know that you'll be shading everything. All right. Now, I'm sure you recognize that. I believe you were asked the question on this in one of your tests. More like, if I'm going to draw it again, let me try and give you how it's going to look. It's obviously going to be the whole thing. So it's going to be, look at it, event A or event B or both. Look at it. This whole thing here is event A, or it could be event B, or it could be both. Or you can see that all of them are represented under union of A and B. Now, let's write the formula for A union B. Then we'll relate it back to this diagram we just drew. The probability of A union B is equals to the probability of A plus the probability of B minus the probability of A intersection B. Can you see this? That means if you are told to find the union of two events in any question, this is what you are going, this is the formula you're going to apply. You need to note this formula, albeit you don't have to really cram it. I can explain to you right now what's happening, how we got this formula. We'll explain that to you right now. And then you will know how to use the concept for any other scenario. So if you have a question that has to do with A union B, this is the formula. Please note that because we'll be solving questions on it. All right. Now, let me tell you guys how we brought about this formula. Since you understand the concept around union of under set theory, we have the whole of this circle, this whole thing now that I'm circling around as probability of A. All right, because this is A. We did not say A only. I'm sure you recognize that A only is this place apart from the intersection. All right. Now, apart from this intersection, this will be A only. But if we just said A without specifying only, this whole circle is what we are identifying with. If we said B without mentioning the word only, this whole circle, including the intersection, is what we call B, probability of B. Now, if we said probability of A intersection B, this will be the place. All right. Now, look at how we're able to carve out this formula for probability of A union B. We went on to say probability of A, this circle, plus probability of B, this circle. But if you notice something that has happened, and overlapping has happened already, because we have represented probability of A union intersect B twice. Because when we said probability of A, look at, we drew the circle. Inside this circle, there was A union B, A intersection B there, when we were drawing probability of A. Now, when we said probability of B, we also still drew that same circle, and we also now included A intersection B again. So obviously, we are now having this intersection happening in both when we dealt with A and when we dealt with B. So we need to, and we only needed one, because don't forget, the whole drawing, when we were drawing, we shaded the part for A, we shaded the part for intersection, shaded the part for. So we only need one of it. That's why we went on to subtract one of it here. That's why you have this this formula this way. Because if you went on to just say probability of A plus probability of B, you would have included this intersection twice. Of course, when you're dealing with probability of A, it will have been there. When you're dealing with probability of B, it will have been there. So you just need to remove one of it. That was how we came about this. Now, I now want us to go quickly to that. For the reason why I did this is because you will see an example where you're dealing with 3 events. So guys, I want you to do something for me quickly. Write in your notes. Go on and give me what is going to be probability of A union B union C. What's going to be this? What's going to be probability of A union B union C? Very, very vital for you to understand all what I just explained. Use it to bring out the probability of A union B union C. So guys, I will be waiting for the answer. So we are looking for the formula for probability of A union B union C. So you already got that probability of A union B is equals to probability of A plus probability of B minus probability of A intersection B. And I already explained how that really happened. All right. Now, I want you now to tell me what's going to be the scenario when we're dealing with probability of A union B union C. This is what I asked you to find. Can anybody give me the answer yet? Make use of your diagram to get this. Anybody? Okay, I saw someone there. Now I can see somebody writing probability of A, probability of B, minus probability of, okay. Now, that was not correct. Unnamed also was not correct. Okay, no, I've not seen any answer there. This is the reason why I try to explain it to you, because I don't want them to confuse you with any kind of Okay. Somebody, okay. Guys, pay attention. This is very vital. Look at something. Let's draw. Let's draw quickly. We have this, we have this, we have this. It's easy to just give you the formula, but I want you to understand how the formula was derived so that you can easily understand this far better. So you want to find probability of A union B union C. Obviously, it will be the shading of everything here. I'm sure you know that already. Anybody confused about that? Huh? You want to find A union B union in terms of drawing the diagram, you want to shade all of this, right? Is there anybody that is confused about that? Now, if you go on to identify what's going on here, if I want to bring out this, the first thing I want to say is, let's say this was A, this was B, this was C. Probability of A plus probability of B plus probability of C. Now, if you go on to say probability of A plus probability of B probability of C, you would have made a mistake in the sense that you would have been adding many of them twice. Look at this one now. If I do like this, A and C, when I said probability of, or let me do for A and B first, this probability of A, this probability of B, this intersection of A and B happened when I did for A, happened for when I did for B. So I need to subtract one of it. All right. So I'm going to subtract just one of that, probability of A intersection B, so that it can balance up well. How I got that was that if I do the circle around A, I involve the intersection of A and B. If I do the circle around B, I am also still involving the intersection between A and B. So I remove one of it to balance everything up. Now, for A and C, if I do for A with C, when I did for A, I had A and A intersection C. When I did for C, I still had A intersection C there. So I remove one of it also. All right. Now, I have that for B and C. When I do for B, I have this intersection there. When I do for C, I have this intersection also there. So I want to remove one of it also. Sorry, B now. B intersection C. Now, can you people tell me what's going to happen with this last middle part? This middle one, which is the intersection of A, B, and C. So what are you going to do with probability of A intersection B intersection C? Some people want to say we should subtract it. Of course, you cannot subtract it. The reason is because from everything we have done here, we have removed all the intersection. You know, when you did for A and B, you removed the intersection there. So anyway, just because I feel many of you are not very, you're not able to follow along, you're going to be adding it anyway because you have thrown it away. So you're going to bring it back. Everything you have done here has thrown it away. Everything you did here threw this intersection, intersection of the three away. So this is the formula for A union B union C. Note this, all right? Note this, you are going to be adding, so this is beautiful. This is what you're going to use. And let me quickly tell you, there are questions like this that comes out for your level. So make sure you know this formula. You'll be needing it some days. So if you want to cram it, go on to cram it. But if you want to understand the way I just explained it, that's also going to be very great. Good, so that at least you are able to always get your answer. So, all right, now it's time to get into lots of solving questions. All right, it's time to solve lots of questions. So make sure you note this formula, please. You'll be seeing it in usage. First question, guys, union of events. Are you guys ready? Okay, so let's see the first question under union of events. We have nah, you are not right, all right. The question is it's not going to be tough at all. It's actually quite simple. You don't need to be afraid at all. It's quite very simple. Okay, so a die is rolled, and event A was 2, 4, 6. Event B was 1, 2, 3. These are cheap questions. You know the way we do it. Uh we start from the easy ones, then we graduate to uh okay. So the first question is for you to find A union B, and question number B was for you to find A intersection B. What's the answer? Uh, for A union B, obviously, these are not things I expect you to have any issue with. That will be, you know all this before. That will be 1, 2, 3, 4, and 6. And for the intersect, that will be 2. All right. Okay. This is just warm up. All right. This is just warm up. Uh guys, a card is drawn from a standard deck, and event A was card is a art, and event B is card is a king. So do the same thing, find A union B and find A intersection B. So what do you get as your answer for the union of these two events? The first thing you have to find out is card is a heart. So your heart cards, how many you have? 13 cards there, am I right? You have 13 cards. And for your king, of course, in the whole pack of cards, you have 4 cards there. So if you're going to have the union of these two cards, of course, you'll be having a total of how many cards? Let me see what your answer here is going to be. I want to see who is going to get it. What's going to be the union of these two? And what's going to be the intersection of these two? Let me get your answers. Okay, is somebody saying the first one is what? Okay, so for the first one, your union will actually be it cannot somebody may want to say intersection the addition of these two, but that will not be the case because one of the cards here is actually a heart, and you understand the theory of union. You don't repeat the card, so there is a heart card that is part of this king, so you only be having 16 cards here. And for the intersection, you only have one card that is both in A and B, so we have just one card represented there. All these questions are too simple, right? I'm sure you guys are feeling this is too simple. So should we get into technical ones? All right, in a class of 40, 22 like mathematics. In a class of 40, 22 like mathematics, 18 like English, 10 like both. In a class of 40 students, of course, 22 likes mathematics, 18 likes English, and we have 10 liking both of them. So the question is for you to find the number who likes at least one. And the second question is for you to find a number who likes neither. So you're getting into the meat of combination of events right now. The rest the last ones we just did were just introduction, all right? So in a class of 40, 22 likes maths, 18 likes English, 10 likes both. What's the number of people who like at least one? All right, let me introduce you to the use of this word, at least one. Remember when I told you, when I was discussing about union of events, I'm sure you guys should be able to recollect that I told you that union represents either A or B or both. You can see from this statement that this obviously implies that at least one. At least one. You can see a way of saying what I just said here, A or B or both, is also to say at least one. Because if A or B or both occurs, that means at least one occurred. So now, when you're asked to find a number who likes at least one, that means you are told to find, let's use event A as maths, and let's use event B as English. So that means we have 22 for maths and 18 for English. And we have the number that has both of them. That will be the intersection. That's what both represent, being 10. All right. Now, you want to find probability, or sorry, the number who likes at least one. That means you are looking for A union B. All right. And you can recollect, for you to find the number of this, of course, you use that formula, which would be the n of A plus n of B minus n of A intersection B. Because this n A union B, I told you already, is at least one. So this will be obviously 22 plus 18 minus 10. And that should give you a total of 30. All right. Now, do you guys really understand that? Does it make sense? Were you able to follow? Let me get your feedback. Do you guys understand what I just said, what I just explained? For the second question, I said neither. Okay, let me try and recap a bit. Look at it. We're dealing with a word problem. The question was for us to find a number who likes at least one. I went back to the initial introduction to union of events, where I told you that union of events represents you saying event A or event B or both of them. That means both of them happening. That's the intersection of both of them. Of course, A intersection B. I said a way of saying that is also to say at least one, because this statement highlights that at least one happened. At least one is this. At least one. A, if A happened, at least one has happened. If B happened, the meaning of union is that at least A must happen or B happens or both. That's at least one of them happening. All right. Now, looking at this question now, you're dealing with numbers here, not yet probability. All right. You're not dealing with probability yet. You have 40 as the total number. That's the number of elements of the sample space, as the case may be. The event space for mathematics are 22, and the one for English was 18, and the one for maths intersection English was 10. Now, the question did not ask you to find probability. You're just dealing with numbers here. Numbers of elements. So you can also apply this formula using numbers. All right. It's still the same thing. It still works the same way. All right. It still works the same way. This works the same way with the probability formula. So all you have to do is to say the number of elements for maths, of course, number of elements for English, number of elements for the intersection of both of them. Using this formula I gave you already earlier, you go on to find this. I told you A union B represents at least one. The question says number who likes at least one. Number who likes at least one. This will be number for maths plus number for English minus number for both. And that way you're going to get the answer to be 30. You understand that the reason why we are giving you this introduction is because there is a time when you really need to make use of all this. So these are just peripherals. You get into questions where you would understand the reason why you would be able to you see why you would need to make use of all these concepts. Now for the neither, I'm sure you know that neither, if at least one happened, looking at our understanding of complementary events. So we have at least one as an event. Guys, what's going to be the complement of this event? The complement is obviously going to be none or neither. Right? So in this case now, we have the total number to be 40. If at least one was 30. So what would be neither? Because at least none plus neither must give you the total. So in this case, x here will be 40 minus 30. That will be 10. All right. This is just introduction. Let's move on. You will see more questions that will give you better understanding. Now look at this question very quickly. We have the probability of A being equals to 0.5, probability of B being equals to 0.4, probability of A intersection B being 0.2. You have to find the probability of A union B. Let's find the probability of A union B. I don't expect you to use you should use probably just 5 seconds to solve this. All right. Looking at this formula now, you have to apply, of course, the formula for union. A union B was given as probability of A plus probability of B minus probability of A intersection B. This will obviously be 0.5 plus 0.4 minus 0.2. That will be 0.9 minus 0.2. That will give you 0.7. All right, good. Another quick one. If probability of A is 0.6, if probability of B is 0.5, probability of A, just I want you guys to get a bit familiar with the formula. So let me just change this right here. So the same question, find A union B. So probability of A is 0.6, probability of B is 0.5, probability of A intersection B is 0.3. What is A union B? Okay, 0.8. You follow the same process, that will be 0.6 plus 0.5 minus 0.3. That will be 1.1 minus 0.3. That will be 0.8. Good. Now look at this one, probably similar but of a different flavor. The probability of A is 0.7, probability of B is 0.6, and probability of A union B is 0.9. I want you to find probability of A intersection B. What's probability of A intersection B? What's the probability of A intersection B? Any answer yet? Okay. All right. 0.4 is the answer as I'm seeing. Of course, to find, you know that probability of A union B is equals to probability of A plus probability of B minus probability of A intersection B. So obviously this will just be probability of A intersection B being equals to 0.7 plus 0.6 minus 0.9. And that will give you a total of 0.4. So I'm sure you can relate quickly to this formula. That was the whole goal for that. Now look at this word problem. In a school, 60% play football, 60% play football, 40% play basketball, 25% play both. Find the probability a student play at least one. So find the probability a student play at least one. All right. That's the question. You have a school, 60% play football, 40% play basketball, 25 play both. What's find probability that a student play at least one? Okay. I like that some of you, I should believe every one of you are flowing at this point because we're already moving deeper. All right. So when you have the event for football, you're dealing with 60%. And you can actually convert this because it's more like saying the probability of football, let's call it event A, is 60 out of the whole, which is 0.6. The probability of basketball is 25 out of the whole. Is it 25? Sorry, 40 out of the whole, which was 100, obviously. That was 0.4. The probability of playing both, that's probability of A intersection B, was 25 out of the whole, which was 100. That's 0.25. So for you to find the probability of at least one, I told you that will signify probability of A union B. Probability of A union B is probability of A plus probability of B minus probability of A intersection B. That will be 0.6 plus 0.4 minus 0.25. That will be 0.75. All right? 0.75. In a group of 100 people, 45 drink tea, 55 drink coffee, 20 drink both. How many drink neither? How many drink neither? Pay attention to the question, please. Don't match things up. So you're told that in a group of 100 people, so in a group of 100 people, 45 drink tea, 55 drink coffee, 20 drink both. The question asks you to find how many. Always understand the question, how many. In this case, how many, not probability here. How many? We're dealing with numbers here. How many? How many drink neither? Any answer there? The question said how many drink neither. You have to be very careful of the context of the question. 25, some people said 25, someone said 20. All right, let's look at it together. So we have a group of 100 people, 45 drink tea, 55 drink coffee, 20 drink both. All right, how many drink neither? Now, neither and at least one are complementary events. None and at least one. They are both complementary events. I think I've explained that earlier. So when you see neither somewhere, you need to understand that the complement of neither, it will be at least one. This will obviously give you the entire sample space, as I explained earlier in this class. So you're told to find how many drink neither. You can go on to find at least one. The number of people that drink at least one. That will help you to find for neither. Because all you have to do to get neither would be subtracting the whole number of elements in the sample space minus at least one. You get neither that way. So probability, the number of elements of the number of people that at least one, of course, you know that similar with you saying A union B. I explained that already. So you want to find the union of the number of people that has the union. That means at least one. I explained that already. So for this, obviously, what you have to do is, what's the number of people for event A? Let's call drinking tea event A, plus the number of people for event B. Let's call it drinking coffee, then minus both. That will be the intersection, obviously. So for the event A, we had 45 there. For event B, we had 55. For both, we had 20. So this obviously gave you a total of 80, all right? This is 100 minus 20, 80. Now, this is not the answer to the question. The question said how many drink neither. This was the answer for at least one, the union. So for you to find neither, you needed to understand this concept right here. So obviously, neither, the number of people, number of elements in the event space of neither, plus the number of at least one, must give you the number of elements in the whole sample space, which was 100. So obviously, you know that this number of neither plus 80, which you have gotten as 80, should be equals to 100. So therefore, the number of people that had neither will be equals to 100 minus 80, which will be 20. All right? That's the way you solve these questions. That's why I told you guys to pay real attention. Let's do another one and let me see how you fare with this. Probability a student pass math is 0.8. Probability a student pass math is 0.8. Probability a student pass math is 0.8. Let's call it probability a student pass math is 0.8. Probability a student pass English is 0.7. The probability that a student pass both, that means maths and English, is 0.6. Find probability that the student passes at least one. Find probability that a student passes at least one. Now, you can understand from all this expose I'm giving you, if you do not understand the use of all these words, at least one, you could get very lost in probability. This questionnaire is very simple for those of you that have been following. But imagine someone doesn't really understand the use of this word, at least one. You would have seen this question as a very big deal, which is not. It's a very simple question. And I'm expecting to see lots of answers in the comment section. So obviously you are told to find probability of maths union English. That's the meaning of at least one. I said that already. That will be probability of maths plus probability of English minus probability of maths intersection English. That will be 0.8 plus 0.7 minus 0.6. I'm sure if you do that, you will get 0.9. All right? So you have to be very careful of whatever the word problem was so that you do not go wrong. Word problems are very key. Now look at this. In a survey, 70% uses WhatsApp, 50% uses Instagram, 30% uses both. All right? In a survey, 70% uses WhatsApp, 50% uses Instagram, 30% use both. Find probability a person uses at least one. I believe by now we should be getting people with lots of understanding of this at this time. So in a survey, we have 70% for WhatsApp. We have 50% using Instagram rather. And we have 30% using both. So the question was for you to find probability a person uses at least one. That means you are asked to find probability of WhatsApp union Instagram. And of course, you know that this would be, of course, this will be probability of WhatsApp plus probability of Instagram minus probability of the intersection of both. Probability of WhatsApp is 70%. That's 70 over 100. That's 0.7. Probability of Instagram is 50 over 100. That's 0.5. Of course, you understand why it's that. That's 50 out of 100. Meaning of percentage is that the number of elements in sample space was 100. 50 out of them used Instagram. That's how you interpret the percentage. And this will be 0.3. If you do this, this will give you a total of 0.9. Let me see how you solve this one. A number is chosen from 1 to 50. A number is chosen from 1 to 50. A number is chosen from 1 to 50. If you are told to find probability, please make sure your value is between 0 and 1. You don't have to put 90 as your answer if you are asked to find the probability, because the question also find the probability student passes at least 1. In that case, your answer must be between 0 and 1. Anything outside 1 or 0 or that bandwidth I just mentioned, it's not correct. All right. So number is chosen from 1 to 50. And of course, event A represented multiple of 3. And event B represents multiple of 7. So the question is find the probability that the number chosen is in A union B. That's the question. So you are asked to find the probability that it is in A union B. So they said the number is chosen at random from 1 to 50. A represented the multiple of 3, B represented the multiple of 7. The question was for you to find the probability that this number chosen is in A union B. What's your answer to that? Do we have an answer quickly? All right. If you look at this question, one thing you can see is you need to bring out the element for event A and the element for event B. Of course, multiples of 3 between 1 to 50. If you go on to check it out, you will see a total of 16 of them. You can go on 3 times 1, 3 times 2, of course, 3 times 12, 36. You go on and on. When you get to 3 times 16, that will be 48. So you know that there are 16 numbers that are multiples of 3 in between 150. For event B, you have just 7 of them. Of course, you know multiples of 7, 7 times 1, 7 times 2, 7 times 7 is 49. So you only have 7 of them. All right. Now you are to find A union B, and don't forget the formula for A union B is the probability of this will obviously be probability of A plus probability of B minus probability of A intersection B. So you have to go on to find the multiple that is both common with 3 and 7. The intersection, that means probability of A intersection B. Now, guys, the easy way to do that is for you to just go on to find the multiple of 21, because the multiple of 21 will be what will give me. Of course, if you want to go on to write all these things out and be looking for them in order to find your intersection, that's still fine. But of course, you don't have to do that. To find the multiple of the intersection between 3 and 7, just go on to find the multiple of 21. That's what will be common between both in both A and B. So the multiple common between two of them, you only have 2 of them. That will be obviously 21 and 42. I told you, for you to find this intersection, just go on to find a multiple of 21. And the multiple of 21, we have 21 and 42. So that there are just 2 elements in that. You are going to confirm this if this is correct, of course. So go on to find the probability of all this. You know obviously that this will be, the probability of A will be 16 over 50. Probability of B will be 7 over 50. These are all just numbers. We did this yesterday and day before yesterday. When you're dealing with, these are just the number of elements in the event space. This is n of A. This is n of B. And this is, sorry, this is not probability. This is n of this. So obviously, for you to find the probability will be, you know, the n of S is obviously 50, right? The number of elements in the sample space is 50. So the probability of A will be 16, that's n of A, over n of S, which is 50. That of B will be 7 over 50 also. And that of the intersection will be 2 over 50. If you go on to solve all this, you should get a total of 21 over 50. All right, you can see how nice and simple all this is. Now, let me see how challenging these questions will be to you. I'll be so glad to see if you guys can rock it very easily. In a class of 80 students, 50 offer mathematics, 45 offer physics, 20 offer neither. All right. Find the number offering both. Find the number offering both. Find the number offering both. In a class of 80, we have 50 doing maths. We have 45 doing physics. We have 20 doing neither. So you have to find the number offering both. Can I get the answer quickly? All right. Of course, the solution to that obviously is just applying the general formula. I told you guys already, n of A union B is equals to n of A plus n of B minus n of A intersection B. This is what you are looking for, n of A intersection B, offering both. Now, if you look at this, you have n of A union B. How do you get n of A union B? That's the first question you have to be able to identify. How do you get n of A union B? Don't forget, n of A union B is at least. So how do you get that right here? In a class of 80, all right? In a class of 80, the question said 50 did math, 45 did physics, 20 did neither. 20 did neither. I told you guys already, in a question like this, neither plus at least 1 will always give me the total number of elements in the sample space. You know, all these little things are very vital for you to be able to get your final answer. So Neither plus at least one, they are both complementary events, and they must always give you the whole of the sample space. You have your number for neither, but you do not have for at least one. You do not know this one. But you know your number of elements of your sample space to be 80. So obviously you can get the at least one from here. At least one will be 80 minus 20. That will give me 60. All right. So that means N of A union B, which is, of course, that's, we already know that this is read as at least one also. This is also at least one. So this obviously is 80 being equals to N of A, 50, that's the first one, that of physics, 45, and then that of both is what you are looking for. You go on to solve this. This will be obviously 95, 80 minus x. So x obviously will be equals to, sorry, I said 80 here, not, this is 60. We got 60, not 80. So x here will be 95 minus 60. And this will give you a total of 35. This is how you crack questions around this. You see, how many of you got this question, by the way? How many of you was able to get this? So the main key and the main testing in this question was you being able to bring out at least one from neither being given. I'm sure if I gave you at least one, you could have gotten both easily. But you're not given at least one. You were given neither. So you need to use this understanding of complementary events to go on to find for at least one. Then thereafter, you can apply it, the formula, to get for both. That was the main testing that happened there. Now look at probability of A is 0.7. Probability of A is 0.7. Probability of B is 0.6. Probability of neither now is 0.1. Now to find probability of A intersection B. So what do you do here, guys? Let me see if you can crack this up also. Probability of A is 0.7. Probability of B is 0.6. Probability of neither is 0.1. Probability of A intersection B is what you are asked to find. Okay. All right. Now look at this question. Just like the other one we just solved, probability of neither was given as 0.1. So obviously, probability of A union B, which is for at least one, will be 1 minus 0.1. I told you guys already, when you're dealing with these two events, neither and at least one, this is for at least one. Union, I told you already, is what signifies at least one. Probability of neither plus probability of at least one should always give you 1 because both of them are complementary events. And the addition of two complementary events, A and its complement, gives you 1. So obviously, if this was A, let's say this was 0.1, let's say this was the one you were looking for, of course, your x will be 1 minus 0.1. That's how I got this right here. So now you have to find the probability of both. Probability of this one is obviously 0.9. So 0.9 is equals to probability of A 0.7 plus probability of B 0.6 minus probability of both, which is what you are looking for. Probably I just write it in full. Probability of A intersection B. Looking at this is 0.9 equals to 1.3 minus probability of A intersection B. Obviously, you can see that probability of A intersection B right here will be 1.3 minus 0.9, and that will be 0.4. You can see how nice and simple this is. You just need to follow the concept. And those of you talking about sets and Venn diagrams, of course, you can use any method you want to use, guys. It's open, but one reason why we have to build all this up is because you need to always have the right there will be a part in probability where you would need all of this knowledge. So that's why you have to understand this also. So two dice are thrown. This question will shake many people, I'm sure of that. Two dice are thrown. Now look at what happened. A was the sum greater than or equals to 10. B was equals to sum being even. So two dice are thrown. So the question is for you to find probability of A intersection B. We're almost done, guys. Let me exhaust. It's just some probably like 2 more questions. I want to exhaust this, guys, so that we don't come back to union or intersection of events. We still have a lot to cover, of course, not this night. Two dice are thrown. Let A be sum greater than or equals to 10, and let B be sum is even. What's probability of A intersection B? Can you guys give me that quickly? So when you toss two dice up, we said the event of sum being greater than or equals to 10 was the first event, and then sum being even was the second event. What's the probability of these two events, the intersection of these two events? Okay, we have 0.4, someone wrote 0.4, someone wrote 1 over 9, somebody wrote 0.111, somebody wrote 1 over 9. Okay, let's try and do it very quickly. Look at the first thing you want to talk about is the event A, right? What are the possible outcomes that bring sum greater than or equals to 10? We say greater than or equals to 10. Greater than or equals to 10. That means we have 10 included, we have 11 included, we have 12 included. How do we have 12 included? Because we can have, look at when you toss two dice up. I'm sure we have done this before to bring out all the elements of the sample space. I'm sure you guys recollect you can have 1, 2, you can have 3, 4, and all those many things. The highest you can have is actually 6, 6. If you remember, you can have 5, 6, you can have 4, 6. So this gives you 10, this gives you 11, this gives you 12. So the highest you can have is 12. And since you're dealing with greater than or equal to 10, this is going to be the highest. Now the question is, how many events in your sample space was sum being equals to 10? That's the first one. Equals to 10, obviously, we have event 4,6. We have 5,5. We have event 6,4. These are all events that can occur that gives you the sum of 10. For that of 11, we have 5,6 and we have 6,5. Of course, that's only 2 events happening there. And for that of 12, we have just 1, 6,6. So you can see that the total possible outcomes for this event A, because this one was actually, you can see 3 possible outcomes here. We can see 2 possible outcomes here. We can see 1 possible outcome here. So the total number of elements in this event A will be equals to 6. All right. Now, for that of sum being even, what do you feel will be the answer for sum being even? Of course, for your sum being even, don't forget, this sum being even is related with this event. All right, the following the greater than or equals to, then sum being even, we have two possible outcomes there. We have 10, of course 10 is even, and we have 12 being even. So for 10 we have three possible outcomes, obviously, as we have done, and for 12 we have just one possible outcome. So totally we have the event B, we have a total of 4. All right, now looking at what we have right here, it is very now possible to solve, given that I've been able to bring out the two events. So this is the number of elements for event A and for event B. So for us to find A intersection B, if you look at this intersection B, event A and event B, what's the intersection? What comes together? What's the number of elements of the intersection A intersection B? Look at this. This is the first event, A. This second event, the one that was even, we had 3 here that was also common here. We also had this 2 of 1 here that was also common here. That means we had a total of 4 happening there. We had a total of 4 happening there. All right. Now, for you to find the probability of A intersection B, all you have to do is use the number of elements of A intersection B over the number of elements of the sample space. That will be 4 over the sample space, obviously, when 2 dice are thrown, is 36. This will give you 1 over 9. Let me give you a take-home assignment because of time, and we'll start from there tomorrow. So take this and let me see how you fare with it. So we're counting from 1 to 100. Guys, you can write this down somewhere. We have 2 events, multiple of 2 as event A, and multiple of 5 as event B. Find the probability a number is divisible by 2 or 5. Find the probability a number is divisible by 2 or 5. So we're counting from 1 to 100. The first event is multiple of 2. The second event is multiple of 5. Find the probability a number is divisible by 2 or 5. We're counting from 1 to 10. Sorry, from 1 to 100. First event, multiple of 2. Second event, multiple of 5. Find the probability a number is divisible by 2 or 5. Find the probability a number is divisible by 2 or 5. So guys, we still have more questions. Of course, this video will be available tomorrow. So what you have to do now is to go through this and make sure you consolidate your knowledge on this. We have independent events, we have mutually exclusive events, and we have conditional probability. This is very, very vital to understand. So all you have to do now is to make sure you stick with the flow. I will advise this video should be available before latest by 12 p.m. tomorrow. I will really advise if you can go through it before the class tomorrow, so you can consolidate anything that you are still not yet grasping. It's very simple, very, 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 very simple, I can assure you. And tomorrow we would see. Hopefully, I'm not sure we can finish it tomorrow, but let's see how far we can go tomorrow. All right, thank you guys for joining. It's been a pleasant pleasure to have you. I really hope you get the best out of this and you will come out victoriously in your exam. Thank you guys. All right. Thank you guys. Take care of yourself. Bye bye.